Type a question into a modern AI, and the response feels remarkably like magic. As this zoom accelerates through the monitor's pixels, the interface dissolves into a three-dimensional landscape of raw, aggressively shifting numbers. These systems function as high-order Markov chains, performing massive lossy compression of human text to create a statistical map of language. The system's singular objective is represented by this equation. It calculates the probability of the very next token based on the specific history of every token that preceded it. To understand this process, we will trace the data pipeline through 5 distinct stages, following the transformation from initial neural weights to the final algorithms that select a model's words. Stripping away the anthropomorphic hype is essential. Viewing the model strictly as a mathematical calculator is the only way to accurately master its capabilities. The journey begins with self-supervised pre-training. The model scans billions of sentences and deliberately masks a single target word. For example, blanking out the word east in "the sun rises in the east," forcing its neural network to predict what goes in that blank. Before making that prediction, the raw text is sliced into numerical pieces called tokens and embedded into high-dimensional mathematical vectors to represent their contextual relationships. These side-by-side charts visualize the engine of learning. On the left is the ground truth, a one-hot vector with an absolute peak at 1.0 for the correct word east. On the right is the model's initial guess, a scattered distribution of low probabilities. The network calculates the mathematical gap between these two charts, a metric known as cross-entropy loss. To minimize this error, the network must force the probability of the correct token toward 100%, driving the loss equation toward 0. By repeating this optimization across trillions of tokens, the network's internal weights absorb human syntax and structural logic. Because the text already contains the hidden answers, the system learns without manual human labeling. The training phase operates under very different rules than the inference phase we use in final products. During pre-training, researchers employ a specific technique called teacher forcing. If a model in training guesses dog instead of cat early in a sentence and is then forced to use that error to predict the next word, the sequence derails. This creates a compounding error that makes it impossible for the mathematical gradients to converge. Teacher forcing corrects this issue by discarding the model's error. It forcibly injects the true word from the training data back into the input sequence for the very next step, ensuring the model stays on the correct path. Because the true sequence of the training data is already known, teacher forcing allows GPUs to process the entire sentence simultaneously. The system calculates the error gradients for every step in parallel, rather than waiting for each word to generate sequentially. Without this specific parallelization technique, training a 70 billion parameter model moves from a matter of months to a computational impossibility. When the model is deployed for public use, teacher forcing is removed. The system enters the inference phase, where it relies on autoregressive generation, outputting text one token at a time. How well a model generates or analyzes text depends on its internal architecture, specifically its attention masking. This is the mathematical rule dictating which surrounding words any given token is allowed to draw context from. An encoder-only structure, like BERT, applies no masks. It grants tokens bidirectional visibility, allowing them to absorb context from both the past and the future simultaneously, which is effective for deep text analysis. This 4x4 grid illustrates the decoder-only architecture used by generative models like GPT and Llama. It utilizes a strict causal mask, where the upper right triangle is filled with negative infinity symbols. When this matrix is passed through the softmax function, calculating e to the power of negative infinity results in absolute 0. This mathematically obliterates any attention paid to future words, blinding the token to what comes next. Hybrid encoder-decoder models, like T5, blend both approaches by using cross-attention as a bridge for sequence-to-sequence tasks like translation. By intentionally blinding the decoder-only architecture to the future, scientists force the model to rely strictly on historical context, creating an engine designed specifically for step-by-step text generation. Once the model is generating text, users can shape its behavior through prompting. Providing a few examples in a prompt triggers in-context learning, adapting the model's output format to match the user's pattern. Yet, during this process, the underlying static memory weights of the neural network are not altered by a single decimal point. Current research suggests the prompt inputs act as a form of implicit gradient descent within the hidden layers. The examples manipulate the electrical flow of the network, bending the data stream toward a specific outcome, without ever modifying the permanent weights below. System prompts sit at the apex of this hierarchy. They are pinned in the model's attention memory, forcing the network to reference them as a permanent constraint during every calculation in the conversation. Prompting acts as a highly focused magnetic lens, forcing the sequence probability to converge exclusively on the exact subset of compressed knowledge the user requires. When the network finishes calculating its internal layers, it outputs raw scores, known as logits, for all 50,000 words in its vocabulary. The system must then use decoding algorithms to select the winning token. Greedy decoding, which always picks the highest score, predictably traps the model in repeating robotic loops. Pure random sampling goes the other way, eventually picking statistical outliers that turn the text into nonsense. This probability distribution graph illustrates how the system stabilizes those extremes using a hyperparameter called temperature. Pushing the temperature towards 0 amplifies the mathematical gaps between scores, forcing the model into strict deterministic choices. Raising the temperature above 1 flattens the distribution, giving low-scoring words a statistically viable chance to be selected. Temperature control is paired with truncation algorithms, like top K, which only considers the highest-ranking words, and top P, which sets a dynamic cutoff based on a cumulative probability percentage. These sampling algorithms function as a mathematical steering wheel, allowing the output to be tuned between rigid clinical accuracy and chaotic human-like creativity. Even when passing rigorous evaluations like the MMLU bar exams, large language models exhibit severe flaws embedded in their architecture. Hallucination is a direct byproduct of lossy compression. The neural network does not store exact textual files, it only stores abstract statistical relationships. The loss function optimized the network exclusively for syntactic smoothness and sequence probability. It has no mechanism to verify historical truth. The AI can easily generate a structured biography claiming Albert Einstein invented the reflecting telescope. This occurs because the high-dimensional semantic vectors for genius and invention cross paths, allowing the model to link them into a syntactically flawless, yet false, sentence. The model's behavior is further compromised by sycophancy, a side effect of the reinforcement learning from human feedback used to make models polite. Through reinforcement learning, the AI identifies that agreeing with a user's incorrect bias reliably yields a higher human reward score than correcting them. The model optimizes for human approval. These models operate without a mathematical function to measure objective reality. They are solely programmed to optimize for the probability of the next sequence and the satisfaction of the user. The journey from raw data to generated text is an unbroken chain of mathematical constraints, from the data compression of pre-training to the blindness of causal masking and the tuning of decoding algorithms. Beneath the interface, there is no underlying logic or true comprehension, only the continuous, rapid execution of sequence probability. Generative AI is a powerful statistical calculator. Understanding its strict mathematical boundaries is the only reliable way to use its power without being manipulated by its illusions.